So we're going to discuss all of this together. So this is another very important major theme. So we're going to discuss acids first. Let's talk about acids. So what are acids? Acids are proton donors. So they donate protons. They're proton donors, which means that they produce H+ ions. That's what a proton is. So that is what an acid is. Now, in organic chemistry, you're going to study different types of acids, and even in those different types, there will be different subtypes. Now, the first one is the weakest one. The weakest one is probably an alcohol. An alcohol has acidic properties, but they're very, very weak. So it's a really, really bad acid. So that's the first one. Let's say this is ethanol. That's a normal alcohol. The second one, a slightly stronger version of this is, I mean, we can put water as an in-between thing, like for comparison. We'll have water. Water also ionizes. And then you have phenols. Phenols are also, they also happen to be acidic. So phenols are, let me draw the molecule. So this is what a phenol is. It's a benzene with OH group. So that comes over here. And then you have carboxylic acids. Carboxylic acids, that is, I mean, they're probably the strongest of the organic acids. Now, one thing, make sure you this is clear to you that they're all weak acids. So when I use the word strong or weak, I'm using it as a relative comparison. All of them are weak. All of them are really bad acids. So that is your carboxylic acid. So this is what the trend is. So let me just write the names. You've got alcohols. And remember, these are all different functional groups. This one is phenol. This one is your carboxylic. That's your carboxylic acid. So all of them are weak acids, but the relative strength is when you move towards carboxylic acid, they become stronger acids. So carboxylic acid is relatively the strongest, and ठीक है भास्कर, मैं इसके बाद देखता हूँ एक सेकंड, just right after, at the end of the class, ठीक है, don't disconnect, ठीक है, I'll find the video and post it. So this one is the weakest. This one. So first thing, that's what the comparison is. We're going to discuss the reason why. That's also important. But I'm going to make a table first. I'm going to make a table, and that table is going to have their reactions. Like if I talk about the reactions, then how many columns should that have? I think it should have. We can have water in the middle, and we can also have. So that's one, and it's sodium, 4 columns. Just 1 second. So anyways, that's our table. That's just a comparison table. I'll have normal alcohols in the first one. In the second one, I'll have normal alcohols, and then I'll have phenols in the next box, and I'll have carboxylic acids in the last one. So the strength is increasing. Alcohols, phenols, and carboxylic acids. Let me forget water at the moment. Let's ignore water. Now, the reaction is with sodium. They're all going to react with sodium. Sodium is a reactive group 1 metal. So all of them, they react with sodium. Then they react with bases, NaOH. If I add NaOH, or you can have KOH, a strong alkali. Alcohols are not going to react with a base. And your phenols will react, and your carboxylic acid will also react. And then you have carbonates. If I have sodium carbonate or potassium carbonate or any carbonate, then alcohols will not react. Phenols will also not react, and carboxylic acids would still react. So carboxylic acids are kind of, and we can add ammonia to this as well. If I add ammonia, then with ammonia, carboxylic acids will react. The other ones would definitely not react. So we can extend this to add include ammonia, which is not really required, but that's also an important reaction.
Sid, we need to understand. Sid, we need to understand why they do not react with carbonates or.
We'll discuss that. So the first thing is we're just giving an overview, which is that carboxylic acids are like relatively very strong acids. Okay, remember this thing, they're all weak acids, but carboxylic acids are like proper acids. They undergo all acid reactions. You can react it with a metal, with a strong alkali. I mean, this one is, and let me label this as well. So this one is a reactive. So all three are going to react with reactive metals. With strong alkalis, the first one is not going to react. Then these two are weakly basic. The last two are weakly. They are weak bases, weakly basic. So with these two are not going to react, while carboxylic acid is going to react. Basa, I haven't discussed anything yet. I haven't discussed anything. I'm just so this is just a general overview at the moment. We're going to take a deep dive and discuss each one separately. So this is the broader overview. This is a terrible acid. It barely has any acid reactions. Like, it doesn't react with ammonia. It doesn't react with most of the things. It only reacts with very reactive group 1 metals. Phenols are like something that's in between. It's slightly acidic, very slightly acidic. It's not really going to affect the pH that much. It's still a very terrible acid, but it will react with alkalis. It will dissolve in alkalis, but it will not react with weak bases like sodium carbonates, and carbonates in general are weak bases, and ammonia is a weak base as well. And carboxylic acid, they're going to react with all 4 of them. Okay, so is the general overview clear? So is this clear? Alicia, is this clear? Monia, Ibrar, Mazga, Saim, clear? So
yes.
So now what we're going to do is we're going to talk about each one separately now. Firstly, we're going to start with alcohols, and we're going to discuss why they're such bad acids and why do they not react with pretty much anything. I mean, they barely act as acids. So starting with alcohols. So the first one, so let's talk about alcohols. Now, alcohols, first thing, they're even worse acids compared to water. They even ionize less than water. So they ionize less than water. And what that basically means is if the ionize less than water, and you can, I mean, there would be, if you remember water's ionization, water ionizes, water only produces, like as a reference point, under standard condition, water produces 1 into 10 to the minus 7 mole per dm cube of H plus 1 ions, which is almost negligible. Like, so if they are ionizing even less than water, that means they're terrible acids. So you can't really classify them as acids. I mean, I'll just write that in brackets. I mean, they're such bad acids, you can't even classify them as acids. So they're hardly going to affect the pH. They're hardly going to have any reactions of acids. So how do they ionize? Anything that has OH groups, like a carboxylic acid, a phenol, they all have OH groups. Anything that's got an OH group, the H, there's a chance that the H would break away. So the same is going to happen with alcohols as well. Like if you have ethanol, now there's a chance that this thing, I mean CH3, CH2, and the H plus 1 might break off. Why would it break off? Because I mean, the actual reaction is slightly more complicated. That the reason why it breaks off is, like, if I just draw this, the OH group is kind of polar. I mean, you know, it forms hydrogen bonds. So it's a very, very polar molecule. It's the oxygen has lone pairs. It's got a negative charge. The H has a very strong positive charge. The reason why they ionize in water specifically is that water is a very polar molecule as well. So what happens is that the lone pairs on water they also have a very strong negative charge. So what happens is that that the water molecules are pulling on this H positive. I mean, they're attracting the H positive. The lone pairs and the H positive are attracting each other, while the electrons in the bond are getting repelled by the negative charge on water. So what eventually happens is that sometimes what will happen is that during collisions, when these ethanol molecules and the water molecules are bumping into each other and they're randomly bumping into each other, the positive H might get pulled by the water molecule and the positive H might break away. And H plus ions are not produced. Actually, what happens is, I mean, this is what the actual scenario is, that the water molecules, they end up forming dative bonds with these H plus ions. The H plus ions, they come in and they stick to the water molecule, forming an H3O plus 1 ions. So whenever we write H plus 1 ions, we actually mean this thing. The H plus 1 ion in aqueous state is not really an H plus 1 ion. It's basically an H plus 1 ion that is sticking to a water molecule, and it's actually forming an H3O plus 1 ion. Okay, but this is the simplistic equation that you always write. The blue one is the simplistic equation. If you include the pink one, that's what the actual reaction is. But the overly simplified equation is the blue one that you are familiar with, that ethanol ionizes and releases an H plus 1 ion. Okay, is this clear, this idea?
Yes, sir.
Yes, thank you.
Okay. Sign clear? Sam, is this clear? Omar?
Yes, sir.
Acha. So the point is that the water is the one, and the water is going to do this to every one of them. Okay, remember, the water is going to come in. All these OH bonds are polar. So a lot depends on the polarity of this OH. Like if the OH bond is really polar, this is an OH. I mean, they're all OH groups. Water has an OH itself. So it all depends on the polarity of this OH group. So the whole focus is on this polarity. Like if the H is really positive, then it's going to be really very strongly attracted to the oxygen lone pairs in water molecule, and it's going to ionize and break away even strongly. So a lot depends on this, like what type of OH do you have. So we're now going to discuss why they're terrible acids. But before that, I'm going to write the equation. So because we wrote down the reaction, so alcohols only react with reactive group 1 metals or reactive metals. So alcohols only react with very reactive metals, mainly group 1 metals. And even in that case, the reaction is very, very slow. So you have very, very slight effervescence. So normally with group 1 metals, you have an extremely vigorous reaction. So it's a very slow reaction, and you're only going to see very, very slight effervescence. Hardly any bubbles would be formed. So the reaction is going to be extremely slow. What happens when a metal reacts with an acid? When a metal reacts with an acid, it produces a salt plus H2 gas. So it ends up producing salt plus H2 gas. I think I should add this to the table as well. Like you should know what's going to be produced when you reacted with a metal. Metal plus acid produces hydrogen gas. A metal with a strong alkali is going to produce acid plus base produces salt and water. So it's going to produce water as a byproduct. I mean, sorry, in this case, you won't get anything. So water is going to be produced. And if you react it with a carbonate, it's going to produce water and carbon dioxide. If you remember O levels or AS. So it's going to produce water and carbon dioxide. And the last one produces an ammonium salt. We're going to discuss that later on. So you should know that metal plus acid produces salt plus H2. So with an alcohol, it's the same thing. Let's say you have a sodium metal and it reacts with ethanol, CH3. It's a CH2 and OH. What will happen is, G.
सर अमोनिया और एसिड का रिएक्शन में क्या फॉर्म था वो ऊपर आपने क्या लिखा?
Ammonia plus acid?
जी कार्बोक्सिलिक एसिड बहुत
It's just that carbonates with acids produces salt and water. Bases with acids they produce salt. So carbonates with acids would produce salt, water, and carbon dioxide. Bases with acids would produce salt and water. Metal with acid produces salt plus H2 gas. Okay. Ammonia ka maine kuch nahi likha. Ammonia produces ammonium salt. That's it. So we'll discuss that. We'll write that reaction when we reach that reaction. Okay. But anyways, you've got alcohols only react with very reactive group 1 metals. You should know what the equation is. What will happen is, this is how salts are always produced. That the H in the OH is going to be displaced by the metal. So it's going to become, instead of OH, it would become O minus 1 Na plus 1. So this is how an alcohol is always going to produce it's always going to produce a salt. And over here, you will have hydrogen gas that's going to be produced as a byproduct. So you're going to get lots of, they'll ask you to draw lots of products. So for example, if you have a skeletal formula, and the skeletal formula has this thing, it's got 2 OH groups. Doesn't really matter what type of OH groups they are, whether it's primary, secondary, or tertiary, we don't really care.
Sir,
Haji.
why wouldn't alcohols react with NaOH?
I'm going to discuss that.
Okay.
I still have to discuss why they're terrible acids. I'm just writing equations right now. So we're going to discuss why they're terrible acids. Now, the first thing is, like if you react it with sodium, what will happen is that sodium is going to come in and it's going to displace these hydrogens, and hydrogen gas would be produced as a result. So the salt that would be produced would be this one. Okay, you will have the H will get knocked out. Okay, so you get lots of questions like this. That's wrong. Just 1 second. So the H will get knocked out and you will have sodium ions coming in their place. And remember, this part is ionic. The O is -1 and the Na is +1. And the byproduct would be H2 gas. Okay, so that's one thing. Make sure you remember, you add Na, alcohols will react with it. If you add NaOH, there would be no reaction. With Na, there is going to be a reaction. So is this clear? This thing, writing equations.
Yes, sir, but why you wrote 2 times OH, like in CH3, CH2, only one OH is present?
Nee, a molecule can have many OH groups. No? Like you can have complicated molecules with lots of alcohol groups. So I'm just saying if a molecule has multiple OH groups, it's still an alcohol. This is an alcohol, this is also an alcohol. So the Na will displace this H, it will also displace this H. I mean, there would be two Nas. Is this point clear?
Yes, sir.
Okay, well, the actual molecule can have many OH groups. And the name of this one, okay, if this is ethanol, this would be known as sodium ethoxide. Okay, that's known as sodium ethoxide. So if the first one is ethanol, if it's propanol, then it's going to be propoxide, and so on. If this was methanol, anyways, the name is not that important. They're not going to ask you. Naming of ethoxides is not really part of your syllabus. So now coming to this question, why are they weak acids? So the reason why they are weak acids, and they're going to ask you that. So reason why alcohols are weak acids are very weak acids. Now, it all depends on the ion that is produced. So for example, you have CH3, CH2. The OH ionizes. So the oxygen gets a negative charge and the H plus one gets a positive charge. So the ethanol molecule is ionizing. So it all depends on this thing. How stable is this ion? Now, in the case of alcohols, remember it's again, we did this in electrophilic substitution as well, 3,5 directing and 2,4,6 directing. So the same concept kind of gets applied to this. A carbon chain has an electron donating effect. Whenever you have a carbon chain, it pushes electrons to any group that's attached to it. It's just a very slight effect, not a very major effect. So alkyl chains, and this is the reasoning. So alkyl chains have an electron releasing inductive effect or an electron donating effect. So, and also remember, if you have a bigger alkyl chain, the electron donating effect is going to be bigger. Like if I had 4 carbon atoms over here, the amount of electrons getting pushed onto this oxygen would be even greater. So also remember this, bigger alkyl chains would mean, that would mean even more electron donating effect. So that's the first point that you're going to write. So what will happen to the negative charge over here? Would it be bigger or would it be smaller? Would the charge density increase or would it be lesser? The -1 charge, is it greater or is it smaller? Saim kya hoga?
Greatest.
It's going to be Saim. Is that clear? Umar, is this clear? Munir, is this clear?
Yes, thank you.
So whenever you have a carbon chain, it's got an electron donating or releasing effect, just a very slight one. So the electrons kind of get pushed onto this oxygen and the negative charge becomes even bigger, slightly bigger, not drastically bigger, just slightly bigger. So you're going to write that the CH3, CH2O -1 charge density increases because of the electron donating effect. So that means this negative charge is bigger in size, right? So that means the negative charge is bigger in size. And if it is bigger in size, why would it let the H plus 1 go away? It's going to attract the H plus 1 back again. It will not allow it to go away because there's going to be stronger attraction between the two. The bond between the OH is going to be a lot stronger. because if the charge density over here is bigger, it will attract the H+1 even more strongly. And the chances of the H+1 breaking off or getting released would decrease very drastically. Is that clear? This thing?
Yes,
Please come
sir.
again.
It's just this. You're sure about this, right? The negative charge is bigger in size, right? Because the
Yeah.
electron. So if the negative charge is bigger,
Mm-hmm.
it's not going to release the H+1 because the H+1 is a positive ion. The positive ion would be even more strongly attracted to the negative charge, right?
I'm with you now. Thank you.
Okay, so the point is that it's not going to ionize. It's not going to ionize. Like, I mean, imagine a water molecule trying to pull the H+1 from the other side. So imagine a water molecule is trying to do the exact same thing. It's trying to pull the H+1 from the other side, but the H+1 would not get pulled away. It's going to come back to the, I mean, it's not going to ionize. So the point is, so this is what you're going to write, that the ion, I mean, this ion, its charge density increases. And the wordings that you're going to use is that it becomes unstable. And it becomes unstable. So it becomes unstable and less ionization will happen, mainly because of that. So less ionization happens. So you can say that what you can say is that you can also state that there's a stronger attraction for H+1 ions. For H+1. One second. The combined effect of the Bhaskar, remember there are lots of water molecules. The thing is that imagine an alcohol molecule surrounded by billions of water molecules. Like it's mostly an aqueous solution. Aqueous solution has a lot of water molecules. So don't think that there's only one water molecule that's doing that. Think of it as it's completely surrounded by water molecules. Bhaskar, is that point clear? Achha, so less ionization, stronger attraction for H+1, or you can also state that the OH bond strength increases because of the greater attraction. Now you're going to use the same reasoning every time. We're going to discuss all the other ones, but the reasoning would kind of be almost the same. So remember, bigger negative charge, it's going to be a weak acid. If the negative charge on the OH, like after it ionizes, if it's lesser, then there's going to be more ionization. So make sure you get this logic clear that anything that has an electron donating effect, it's not just alkyl chains, it could be anything. Anything that has electron donating effect, the negative charge when the OH ionizes, it becomes bigger in size. And if it becomes bigger in size, it's not going to let the H+1 go away. It's going to attract it back. It's not going to ionize. It's going to become a very strong conjugate base. It's not going to let go of the H+1 ion. And this is the reasoning that the charge density on the ion increases and it becomes unstable, which is why there's less ionization. There's less ionization, and there's a stronger attraction for H+1 ions. So is the reasoning clear? This one, everyone, is this clear?
Yes, sir.
Thank you.
And I'm going to, because remember they're going to give this question in many different combinations. Like they could present you with lots of scenarios. The key is, I mean, this is the summary for almost all of them. Like everything that we discuss from now on, this is going to be the summary. Electron donating effect. Remember, there's always going to be an OH group. First thing, like all of them, they all have an OH group. So we're all interested in what happens to the OH group, what happens to the OH group, what happens to this OH group. So we're only going to be talking about the same thing. So the summary is, and you can use this general summary, electron donating effect, right? Depending on the group that's attached to it. So if it has electron donating effect, what happens? Charge density on the ion increases. So the negative charge density on the ion it increases. And you're going to add that the ion becomes unstable. And it's going to be a stronger acid, sorry, a weaker acid. So it's going to be a weaker acid, and there's going to be less ionization in it, less ionization or dissociation. So there's going to be less ionization. And the reverse, so this is the same reasoning. The other one is exactly the opposite. If you have a group that has an electron withdrawing effect, so I'll just copy paste whatever we wrote above, but the exact opposite of that. I'll just rub off, just use the opposite words. So in this case, now in this case, the charge density on the ion would decrease. And the ion becomes stable. And it's going to be a stronger acid, and there's going to be more ionization that would happen, or more dissociation would happen. So that's a summary of the reasoning behind the strength of acids. And you're going to use the same reasoning every time to discuss every other molecule or any random molecule that they give. It's not that they could give you any molecule. The reasoning should be exactly the same. So I'm going to discuss the other one now. I'm going to talk about so is this first thing, is the reasoning clear? All clear?
Yes, sir.
So we're going to discuss phenols now. So what's happening with phenols? Phenols.
से फिर हमारे पास वहाँ पे टर्शरी जो वो होते थे कार्बन, टर्शरी कार्बन, वो ज्यादा स्टेबल क्यों होते थे?
नहीं,
उसमें तो इलेक्ट्रॉन डोनेटिंग इफेक्ट ज्यादा होता.
Stable? नहीं, we're not talking about carbocations here, ठीक है? We're not talking about their mechanisms. We're talking about their strength as acids. I mean, like if I have like, I'll apply the same reasoning. Let's say I have a methanol molecule. Can you hear me? इब्रार आवाज आ रही है?
जी अब आ रही है. जी.
अच्छा, so this one. Let's apply the same logic, right? So I've got two alcohols. One of them is a primary alcohol. The other one is a tertiary alcohol. It doesn't really matter whether it's primary or tertiary, right? Remember, we're not talking about carbocation stability. We're not talking about mechanisms here. It's only their strength as acids. So this one will ionize. The H+1 would break away. The oxygen will get a negative charge. The H+1, the H will get a positive charge. This OH will also ionize. The O will get a -1 charge. The H will get a +1 charge, right? So the question now is, which one has more electron donating effect? The left one or the right one? Which one is it? Like, who's got more carbon chains? You've got over here, you've got just one methyl group that's pushing electrons. Over there, you've got 3 carbon chains that all have electron donating effect. So the end result would be that the negative charge over here is going to be, it's going to be larger, it's going to be bigger in size. And because it's relatively speaking, like if you do the comparison, the negative charge over here would be smaller in size, it's going to have a lower charge density. But if you talk about this molecule over here, the negative charge is going to be bigger in size and it's going to have a greater charge density. So the H+1 would be more strongly attracted to the O-1. And it's not going to ionize, it's going to be a weaker acid compared to the first one. And you're going to write this reasoning. You're going to write that the molecule on the right side, this tertiary alcohol, has more alkyl chains, so it's got more electron donating effect, which is why the charge density on the ion with this particular ion, it increases and becomes unstable, and therefore it's a weaker acid and there's less ionization energy. Sorry, not ionization, there's going to be less dissociation or ionization because it's going to have a stronger attraction for H+1. It's not going to let go of the H+1 ion and it's not going to ionize or dissociate. Is that clear? Ibrar, is this clear?
Yes, sir.
So they're going to give you all sorts of combinations. So make sure you remember this stuff. So we're not talking about phenols. Phenols is a benzene with an OH group. And we did discuss that. Let me just make a phenol. So it's simply a benzene with an OH group. And the first question is that they are they only react with, they're stronger than alcohols but weaker than carboxylic acid. So they only react with Na and NOH. They don't react with carbonates. So no reactions with carbonates. Okay, that is not going to happen. Only this. So now, since this is the case, we're just going to quickly write the reaction. Like if I have a phenol and if I reacted with Na or NOH, I pretty much get the same thing. Okay, make sure you know how to write the equation. So that's one. So I'm just going to write two equations. The first one is with Na. So what will happen if it reacts with Na? It's going to form a salt. And the salt is going to be, so the salt is simply going to be the H will get knocked out and Na+1 is going to take its place and hydrogen gas is going to be produced. That's it, that's the reaction. This is known as sodium phenoxide. So if it's formed from phenol, it's going to be phenoxide. And the next one is also kind of the same. Like if you have, so that was with the Na. If you reacted with an alkali, it's going to form the same thing. It's going to form a salt, which is going to be exactly the same. So it's going to be O-1, Na+1, and there's going to be a water molecule that's going to be produced. Okay, those are the two reactions that you should know of about phenols. And the next part is what happens when, so two reactions, Na and NOH, that's two reactions. So remember, whenever you have NOH, like they'll give you a complicated molecule. Okay, maybe let me make one complicated molecule. So if they give you a molecule and they say that, so here's a molecule and let's say there's a carbon chain and there's another So here's your example. Like you have an OH group here, and you have, that's a wrong one again. Just a second. Sorry. Let me just. Anyways, this one. So I've got a molecule here. A slightly more complicated molecule. And I've got an OH group here, and I've got I mean, there's obviously an OH group here as well. And I'm reacting this molecule with NaOH. So which one of the OH groups will form a salt? What do you think? Which ones are phenols and which ones are alcohols? I mean, is this
The top two.
the top two are phenols? Remember, the OH, if it's attached directly to a benzene, that's a phenol OH. This one is an alcohol OH because it's attached to a carbon chain. It's not attached to a benzene. So this one over here is an alcohol. So you get a lot of questions like these. They would give you a molecule, and so is this clear? This thing that this OH is not going to react. Like if you make the salt and water would be produced. The salt that would be produced would be, nothing happens to the alcohol because we just studied that alcohols don't react with NaOH. So it would not do anything over there, but these two will end up forming a salt. And this would be Na+1. This one would be Na+1 as well. Right? Is this clear?
Yes, sir.
So make sure, because remember, you have to figure this out. Lots of combinations they'll give you a lot of questions in a lot of combinations. So we'll continue with this tomorrow then, and we'll discuss why phenols are kind of slightly better acids compared to alcohols. The reasoning is pretty simple because it now has an electron withdrawing effect. So the negative charge over here would actually be after dissociation. Like if I take this alcohol, the negative charge over here is not going to be that strong because the electrons over here would mix up with the benzene electron cloud. But we'll talk about that tomorrow then. Okay, the reasoning why phenols are better than alcohols. Okay, so any questions about this? Is this clear?
Yes, sir. Sir, could you kindly just move the screen a little bit down?
Yeah, I'll share the board link just a second. I mean, open it on a Wapina Sara. It's everything would be given here. I'm sharing the board link. It also has the previous notes as well, except for the electrophilic substitution ones. Okay. So I've shared the board link, but don't open it on your mobile. Open it on a laptop or a desktop. TK, you got the link?
Yes, sir. Thank you.
Okay,
Chalo.
take care.
Allah Hafiz.